So now we're going to be looking at some angular momentum problems. And in general, the quantity for angular momentum is, we use the letter L, and it's I omega. So it means I need the rotational inertia and the angular velocity. A marble rolls down an incline at 30 degrees from rest. What is its acceleration and how far does it go in 3 seconds? Actually, so these first problems are rolling problems. So when you have... when you're looking at something that's rolling, generally down an incline that's 30 degrees, what you're going to do is you're going to do free body diagram. But in the case of a rolling problem, there's a relation. If it rolls without slipping, there's a relationship between its angular acceleration and angular velocity to its linear acceleration and linear velocity. Okay, so I have mg, I have my normal force, and then I have a slight friction force. And the force of friction is necessary in order to cause this thing to rotate, because neither the gravity or the normal force will cause a torque on this thing to cause it to rotate. So only a slight amount of friction is necessary to cause it to rotate. And this frictional force is a static frictional force. It's not a kinetic friction force. It's static friction. And so computing it is actually somewhat not difficult, but you can't just, you have to treat it like a static, not like kinetic friction, which has a constant value. So first I want to set up my orientation. I'm going to say down the ramp, positive x, positive y direction, like that. And I'm going to say, well, the acceleration, the net force down the ramp is equal to mg sine theta minus the force of friction, and that has to equal ma. Okay, and that's its acceleration. So so the other thing with rolling with something is I know the net torque is equal to again, the force of friction is the only force doing a torque, and I do r times the force of friction. So it's the radius of the sphere times the force of friction. That has to equal I alpha. Now the relationship between rolling, like we said before, is the angular. The linear acceleration is equal to alpha times r. Okay, so alpha is equal to a over r, and so that means it's I a over r. Or in other words, the force of friction is going to be I times a over r squared. And so I got to substitute force of friction back into here, and then I can solve for a. So I have mg sine theta minus I a over r squared is equal to ma. And if so at this point, what I have to know is what I is, and I for a uniform sphere, I think it's 2/5 mr squared. So I'm going to use that substitution here. So again, mg sine theta, bring this to the other side, is equal to ma plus I, which is 2/5 mr squared, times a over r squared. R squares cancel, and the m's will cancel out of all of these. So this is g sine theta is equal to a plus 2/5 a, which is 7/5 a, right? And so then a is equal to 5/7 g sine theta. And I actually know what theta is. Theta is 30 degrees, so it's 5/7 times 9.8 times sine of 30 degrees, which is 1/2. And that is 3.5 meters per second squared. Right, is that right? 5 divided by 7 times 9. Okay, all right. Okay, so that's the acceleration, and how far does it go in 3 seconds? This is a kinematics problem. So we would say delta x is v naught t plus 1/2 at squared. The initial velocity is 0, so I just have 1/2 times 3.5 meters per second squared times 3 seconds squared. You get 15.75 meters. Okay. A rigid body with a cylindrical cross-section is released from the top of a 30-degree incline. It rolls 10 meters to the bottom in 2.6 seconds. Find the moment of inertia of the body in terms of mass m and radius r. Okay, so almost identical setup to the previous problem. It's going to roll this way, And the free body diagrams is this, a little bit of friction here, and the normal force, right? These are all the forces. The net force along the ramp, in the direction of the ramp. And the x direction is going to be, remember this, so this is theta here. This side's going to be mg sine theta. So mg sine theta minus force of friction is equal to ma. And then the net torque, only the force of friction does a torque, so it's r times force of friction is equal to I alpha. And so my goal is to figure out what I is. So I, if I solve for this one, is equal to r force of friction over alpha, right? And then I can plug in for I can solve for force of friction here is equal to mg sine theta minus ma. And I can plug that into here, so I'm going to get r times mg sine theta minus ma over alpha. Now, what we need to figure out is what a and alpha are in this instance, right? Because I know the radius, or actually in terms of m and r, I need to know what a and alpha are in terms of this scenario. So we need to look at the information that they give us, because they gave us the angle theta. So it's 10 meters to the bottom in 2.6 seconds. That means I can figure out what its linear acceleration is by kinematics, right? And they've given us time, so delta x, because they gave us time, I'm going to use this equation. And I want to solve for the acceleration. So v naught is 0 in this case. So this is 0 because we starts from rest. So I have 2 delta x over t squared is equal to a. And that's 2 times 10 divided by 2.6 squared. I get 2.96 meters per second squared. So that's a. And then alpha, in a rolling problem, what relates the linear acceleration to the tangential acceleration is just r times alpha is equal to a. So alpha is equal to a over r, which is just 2.96 over r. So if I plug back into here, I'm going to have r times mg sine theta minus ma over a over r. A over r. And so then I can, this is r squared mg sine theta minus ma over a, right? Just flip this and multiply by r. And so then I can plug in this 2.96 for a and sine of theta. And so I'm going to have r squared times m. G times sine theta is 9.8 times sine of 30 degrees is 0.5, so that's 4.9 minus m times 2.96 all over 2.96. So this becomes, I just subtract the 4.9 minus the 2.96. This is going to be 1.94 mr squared over 2.96. And finally, I just divide 1.94 divided by 2.96, and I get 0.6566 mr squared. That would be its rotational inertia. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.